All right, it's my pleasure to introduce the next speaker, Dave Paddock, who I've had the pleasure of working with on and off over the last 10 years on various projects. So Dave earned his BS in Mechanical Systems Engineering at the United States Military Academy at West Point, followed by 5 years of service in the Army, and then joined NASA in 1990. After transitioning to the Mechanical Systems branch in 2000, his work at NASA has been focused on mechanical design, analysis, and manufacturing of aerospace hardware for aircraft, spacecraft, and launch vehicles. Dave has worked with Hypersizer and HyperX software for nearly 20 years, both conceptual and detailed design and fabrication. Today he will talk about one of his most enjoyable projects, affectionately known as Octopants.
Good afternoon on behalf of Dr. Lee, myself, and Trevor Jackson. This was really fun. This is a very fun job we did. Basically, it was the three of us were set free with a clean sheet design from Glenn Research Center. And the guy that was leading us was kind of insane. So he would accept a lot of weird stuff, and that was the wrong thing to tell us. So, but Hypersizer through it made things very speedy for us, so you'll see that. All right, our outline here. I want to begin by describing the bulkhead concept and its role in the overall vehicle. So it was, we came up with several structures, concepts that were fairly different, derived from the design and the analysis requirements. And then I'll show you a few of those models and the finite element models we started with. I'll spend the bulk of the time on the analysis and optimization process we did using Hypersizer. And remember, this is 2015 Hypersizer, in connection with Nastran, which was, of course, still Hyper-FEA. So it was, that part of it was automated really well. So I'll show the results, but I also want to spend a little bit of time showing you the work that, that Mr. Gillespie did and James did on when I gave them the files from 2015, and they said, well, what if we run some of the stuff you did manually in 2015? What if we did that on HyperX? And so they got to play a little bit with that. So I want to show you some of that too. Many of the manual operations we did in 2015 are much quicker now in HyperX. So. All right, so here's the vehicle. You can see much of the program was done right here at Langley. The retrieval arms and mechanisms were done here. But what I'll be briefing today is the mission we got from GRC to help them with the structure of that lower bulkhead, which you can see on your right there. This bulkhead was to be primary load-bearing structure at the base of the module, which almost everything in that bus was mounted at the bottom or had to go, the loads had to go through the bottom of that. Our requirements, and especially the highest load cases, came from the launch vehicle. It was to be designed to launch on a Delta IV Heavy. And so those of you who are familiar with a launch vehicle, the loads are so violent at launch usually, and a lot of the second most are usually at max Q, and it's when it's up higher, but it's going hard and it's trying to break through sound barriers and everything. And that thing, your payload just gets shaken all over the place. So some of the hardest loads to take care of are its own inertial loads, as well as the frequency requirements that it must meet, and that's a minimum first natural frequency for the launch vehicle, so it won't shake itself apart or excite other frequencies down the stack. And that's something that the launch vehicle maker puts out. So right away you can see every pound or ounce you add to your payload is going to raise your loads because they're inertial, and it's also going to hurt you meeting that minimum requirement for natural frequency. But we started by treating the load cases as the primary design driver. We learned along the way that the minimum natural frequency actually overcame that as the driving mass, final mass, as the driver for final mass. As is typical of this type of project, we were given a coarse finite element model of the whole thing there, and CAD models of surrounding parts or pieces of payload that constituted the boundary conditions of our modeling. So this was sort of, when I usually start with a piece of paper, and I'll print out what I got from the CAD, and then I'll start just drawing lines all over the place. So what I wanted to do is go from the hard points on the payload pieces and to visualize where those loads have to finally get to, which is this flange down here that goes to the rest of the rocket. And you get that a lot in these cylindrical launch vehicles. You can see here, this is sort of the studies we went through. On your left, Trevor and I started brainstorming the shell structures we wanted to try to create the load pass to the sidewall of the bus. And in my mind, I was, from lessons learned of previous projects, if I could stay in the solid laminate area of design, so much gets easier, because when you start making sandwich, you've got the testing you have to do, and especially with weird shaped sandwiches, that core is just going to want to tear itself away from the inside. So I was hoping to stay with something that was solid laminate, but at least the shells I started with were. So by far the largest inertial loads were transmitted from the xenon tanks, which are these. And you can see we had 8 of them around, and they're about this big around each. We had several configurations to take on, but I thought I'd do the tallest ones, of course, just to make sure we could cover that. But if you're not familiar with this, you've got Hall thrusters on the bottom that ionize the xenon and create very low force thrust on the vehicle, but it can burn, if you will. It can ionize and push for years. So these are deep space vehicles mostly, because a constant acceleration that you can apply over a long period of time is going to get you very fast, obviously. So I favored the design that would put the composite fibers mostly in tension. And you can kind of see that from the octapants that we chose, is that those heavy xenon tanks accelerating downward are going to put the fibers of the purple section mostly in tension. And I thought that might bias and keep us in the range of solid laminate and still be efficient. We found higher buckling load factors, obviously using the geometry from the outset as compared to the shell geometries that were put in compression. But, and that, of course, makes sense as well, right? Okay, so the left side is the CAD that we handed off to Dr. Lee, who was our primary analyst, and he created the FEM that's on the right-hand side. Nothing so crazy except for all the curvature, right? So this piece, if you've got 2-foot tanks, you can see that this diameter is pretty big. So it's not that small when you're considering a single piece like that, but sometimes it's hard to tell from just pictures, right? Okay, so another thing that I found out was that not a lot of space vehicles were using high modulus fibers for primary structure. And obviously it's a high modulus fiber means it's basically a stiffer fiber, but a lot of times it's a weaker fiber for just in tension mostly. And compression usually tracks almost the same, but but certainly in tension, it can be weaker than intermediate fibers. Well, when I saw this, it's almost a pre-buckled shape, right? Because there's no flats for you, except that plate on the bottom. So I was thinking, well, maybe our buckling would benefit from a high modulus fiber instead, and we're Langley, so let's do something that hasn't always been done, right? My tool has been the PTC family of CAD and FEA mixed in together. It started as Pro Engineer, then was Wildfire, and then now it's Creo. And so I was doing a lot of the shape optimization in that tool by myself, going back and forth, because the parametrics goes to the FEA as well for topology. So this was the shape we ended up handing to Ying-Yong Lee, but I also warned him that I'm still messing with the shape, you know. You can do your FEA, but I'll probably change the shape on you. He's like, thank you very much. But Dr. Lee he wanted to do new stuff too, so he put the high modulus fibers as the primary mix in the early optimizations he was choosing. Another thing I want to point out is that one of the reasons I grabbed onto Hypersizer early was that it was an analysis tool that engineers that got to make design decisions can use. So we love equations in closed form, and that's what the basis of Hypersizer was, of course, and still is. And the documentation of what the tool actually does is right there. It's so transparent. So I keep pushing this as a design tool from the start and not necessarily just an analysis tool. So he was informing me where the trouble spots were, especially in the curvature areas that were troubled. And he'd just show it to me. He could come up with it, even with cycling in Hypersizer. You know, if you've got geometry issues, Hypersizer is not going to be a magic tool that changes that. It's going to show up all the time. So he was able to get back to me and say, hey, I'm not fixing this with layup changes. So I would tweak the shape again and throw it at him, and he would generate his FEM again and then run the Hypersizer. The color coding here, you can see that we've split out the components. You're calling them zones now instead of components, right? So HyperX is zones. So what you're seeing is the various zones that Dr. Lee put in there, because with all the weird changes in curvature, he thought, hey, I better have lots of different zones for this thing, because they're all going to have weird different loads inside of them, so we should size them differently. This is another view of the bulkhead. I wanted to call your attention to the local material coordinate systems on which the Collier staff worked with us extensively. And a lot of it, I think you already had. It was the material coordinate systems that were radial instead of just linear. And at the time, we had great help, because as soon as Dr. Lee mentioned, hey, I don't know how to do this, I don't know if it was brand new at that time, but we were able to incorporate it, and there was a lot of back and forth, which is the strength of this company, is that it's responsive, and you'll write code to change stuff, which is great. It was the first time we had worked with cylindrical material coordinate systems in this software, that is. Okay, for the material properties, you can see the M55J that we, well, can you see this? No, not this one. Anyway, these were, you see it down here. Basically, Dr. Lee created a quasi-isotropic material out of M55J that would respond to just changes in thickness. Because again, 2015, you know, y'all are running millions of iterations these days, but back then it could take a long time. So the more simplification you could put in to make design decisions, the better it was. So he made this material that would still have the high modulus quality to it, but he could just change thicknesses at the outset. So this shows you just one of the components or zones that was at the base of the xenon tanks, the rings that actually grab the bottom of the tank. All right, at this point, Dr. Lee's analysis process, his own personal process, was to run hypersizer with hyper-FEA against the load cases to get strength results, as you see on your left there. Then he would take that solution of thicknesses, again, that was the parameter that was telling him all he needed to know, and he went to Nastran 105 solutions for buckling, making manual changes, as you see in the red in the middle chart, to fix, quote, to fix any buckling issues he had, any lower eigenvalues he had. Then he would take that, once he had that solution, he took that over, he thought he was close, and that's another whole discussion of design, but he went over to run Nastran 103 again, manually adjusting that one panel, panel ID number 4, which is the flat panel on the bottom. By the way, I should have mentioned there's a plastic model of it in the back there. It's a quarter scale. So he ended up fixing that and coming up with a 150-pound bulkhead that, you know, in our opinion was pretty good for that size and on those xenon tanks. Those xenon tanks were carrying, it was like 1,250 kilograms each into launch. So this was his process. And the first time he had inadvertently selected an eigenvalue of 1.54 for the buckling that was low because he didn't incorporate the 1.4 factor safety that you usually do. And this is first iteration stuff. So we were still just learning about the basic shape and everything. This is a little hard to see, but this shows you the buckling areas for the different load cases that we had. And it just brought his attention to where to fix things. And then this is the view of the first mode, second mode, and third mode, natural frequency. And you can see this was an axial load, so you can sort of picture the stuff in the middle that's mounted, breathing up and down along the axial axis. And then the second and third are actually the xenon tanks swaying back and forth. So the pant legs are going in and out at that point. So we went into the second analysis process, and he said, oh, let me bump that up to the 215. It's typical. I think it might have been David Slight that called that out to him when he saw it. And so he cranked that up, and he did the same process again, strength in hypersizer and hyper-FEA, started with the same base model he had, and then he went to meet buckling eigenvalues that were higher. So he had to iterate and change the thicknesses to higher values to get that higher eigenvalue of buckling. Well, when he did, he found out that to get his first mode frequency to meet, he didn't have to make that big of a change to the buckling solutions, but he changed more of the critical pieces. You can see tracking across 03 to 04, 03 to 04. So he's just having to add just a little bit, which kind of tells you, well, that seems to be a more efficient design for frequency if I'm fixing the buckling. And the weird part was that the final solution was 30 pounds lighter than when he did it before with a lower buckling eigenvalue. That was the biggest surprise of this portion of it was we said, wait a minute, you know, you'd think you crank up some requirements and the weight's just naturally going to go up, but obviously not. So the connection between the buckling requirement being cranked higher and meeting the frequency at a lower mass was sort of a revelation to us. Again, here's the second process with the higher eigenvalue for buckling. These are the results. It's pretty much the same locations for each one, and the same mode shapes, at least for the frequency analysis. So here's where James and what's Gillespie's? John, is he here? Hi, John. So he took this over and probably had fun with it because, you know, nerds, that's what we do. He took it over and said, well, let's crank HyperX, crank the whole thing with HyperX. And I gave him all the files we got because the best thing about working at Langley is that if it's an in-house project, it's supposed to be disseminated to everyone in the country to improve on it, use it, or whatever. So I was able to just throw everything I had at these folks. And there were a lot of stuff they had to go through, but quickly, he was able to use the automation of HyperX to get to what took us weeks or months to do when we were working in 2015 and doing a lot of stuff manually. So he was able to do the buckling and frequency optimization through HyperFEA, which I think one of those might have been available back then, but we didn't know how to use it, so that's our fault, right? Not taking his courses. But it was automated for John. And so automatic laminate family creation. I don't think we had families of laminates, and we never really got to that point until we did it later manually for when we wanted to make the unit we made as a prototype. Laminate study tools, I didn't think we certainly didn't have the automation involved with that back then. Ply sequencing and visualization tools, that was me drawing on paper mostly. How is this going to blend into that one? And then, of course, export of the ply books to FiberSim, which I used in conjunction with Creo to create the plies and the ply books and everything. That didn't exist at all back then. So this is pretty neat. Here's some plots of just to show you. This was focused on the frequency, but apparently y'all did it for the buckling as well. But you can see here how it's run in an automated fashion to get to these requirements, the 15.5 hertz requirement in an automated way. So you can go back and forth. And with this automation, I think you'd be able to do a lot more what-ifing than we were. So here you see the total weight was about the same that we got manually, but again, it was driven by the stiffness requirements that the previous analysis put up there. Now you can put in a stiffness requirement in the material properties and it'll drive to that, which I know we didn't have that back then. And then these interleave family laminates to make manufacturing and to see the manufacturing right in front of your face, that's huge. Because again, I was doing these lines in, with colored pens and stuff. So this is awesome. Let's see. So these are the conclusions here that I want to throw at you. We were able to learn really quickly using this tool, and it's because you could get the graphics was huge too, because designers think in cartoons, right? We get glazed over with words, but cartoons we know. So the graphics portion of this tool has always been very strong, and it allows someone sitting there to make decisions very quickly about, that's a problem area. I got to change that, or I got to fix that. The final sentence is the big lesson learned from this presentation, at least this part of the project. We probably would not have stumbled onto it like this, it's staring us in the face without this tool. And that was, and I've done this since, is to adapt our design process so that we look at a sensitivity study of eigenvalue versus natural frequency, which I think would be really much easier now than I've been doing for the past 10 years or so. But it's this artificial creation of different eigenvalues for buckling and seeing what mass comes out when you fix the frequency. So a weird way to look at it. And this kind of a structure, you've almost left strength behind. So what does that tell you? Well, maybe that tells you you go even stiffer with less strength fiber. And we didn't even get to that. So it's, I think that's what I got.